All right, and so now we can look at another trig integral over here, where we are considering that in our integrand we have a power of a cosecant multiplied with some power of a cotangent. And that's the trig integral that we want to specifically get into over here. So our trig integral here involves a cosecant and a cotangent, specifically in the form where it's a power of the cosecant multiplied with a power of the cotangent. They may or may these two powers may or may not be equal. Okay, and so now let's get into it. All right, so now when our power on the cosecant is even, okay, so when this power m is even, then being an even number means m has to equal a multiple of 2. Okay, and so m being an even means m is a multiple of 2. And so in that case right here, I can rewrite this entire integral as an integral of cosecant to some power being a multiple of 2. I'm writing that as a 2k of x, okay, times the cotangent to the power n of x dx. And then further, I am now going to separate out a cosecant square out of that, cosecant to the power 2k. So here I'm looking at cosecant to the power 2k minus 2 of x times cotangent to the n of x times the cosecant square of x. That's what I said earlier. Let's separate out a cosecant square out of that even power on the cosecant. All right, and so now I'm seeing this 2k minus 2 as a 2 multiplied. So right here I'm seeing that as a 2 multiplied with k minus 1 in quantity. Okay, so seeing that power, seeing that the algebraic nature of this power 2k minus 2, I can rewrite in my next step. Think about, we can rewrite this cosecant to the power 2k minus 2 as the cosecant square of x multiplied with the power k minus 1. Okay, that's just the rule, the algebraic rule of powers like that. Okay, so when we have a power and we raise it to another power, the power k minus 1 multiplied with power 2, specifically in this case right here. And that's how I can go back from cosecant to the power 2k minus 2 and be rewriting that as a cosecant square, all in quantity, raised to the power k minus 1. And then the cotangent to the nth power stays the same. And the cosecant square of x that we purposely wrote out, separate out, stays right there. All right. And so now for cosecants, we have an identity. We know from trigonometry that cosecant square of x will equal to 1 plus cotangent squared of x. Okay, this is some known fact right here from trigonometry. So now I can substitute 1 plus cotangent square of x for cosecant square right in this part right here, not the other ones, the one that's inside the bigger power. Okay, and so now I'm going to make my integral to become, okay, so that's the integral 1 plus cotangent square of x raised to the power k minus 1. Okay, and I'm going to multiply with the other part right there. There's a cotangent to the n of x times the cosecant square of x dx. All right. And so now upon arriving at this step right here, where we have produced our integral completely in terms of the cotangent. So 1 plus cotangent square to the power of k minus 1 times the cotangent to the power n of x times the cosecant square of x dx. So once we have arrived here with our general integral, then we can substitute as a general plan right here. We can substitute u for cotangent of x. And then doing that, du dx as the derivative of u right here will become minus cosecant square of x. And then rearranging the differentials, I'm looking at minus du to equal cosecant square of x dx. All right. And so now upon this substitution, now we're going to treat the integral as an integral simply in terms of u. Cotangent now is going to be substituted by u. So I have a 1 plus u squared raised to the power of k minus 1 times, now I have a u to the n substituted for cotangent to the n of x. And now cosecant square of x dx will be substituted by a minus du. A minus du. And so the overall integral, I can now bring that negative sign in front as a coefficient, so making it a negative. Okay? And then now I have the integral 1 plus u squared raised to the power of k minus 1 times u to the n with the du. And so at this point, you have turned your integral into an integral completely in terms of u as a polynomial in terms of u. And so, of course, I'm not saying that we're done here, but that was the general plan of what we can do with this. And so the next step here, you can go ahead and FOIL out this 1 plus u all squared to the power of k minus 1 right there, and distribute in that u to the n. And then you're going to have a polynomial completely in terms of u, where you can do the integration term by term. All right, so that's how we handled a trig integral where it involves a power of the cosecant in product with a power of a cotangent, but specifically when your power on the m, when your power m on the cosecant is even. All right, so now let's dive in an example or two so that you can see how useful this general guideline can be. So right here is a general guideline, and then you will be seeing an actual example where I can point out some specific example. All right. All right, so now we're looking at an example of a trig integral where we have a power of cosecant with a power of the cotangent. And further, we're here at that case where the power on the cosecant is even. And so from the general guideline that I have given, then with this cosecant at the even power right here, we can purposely rewrite our integral as following. I'm going to write that as a cosecant to the fourth of x times a cotangent cube of x. But I isolate out a power 2 of the cosecant. So instead of writing that totally as cosecant to the 6, I separated out a cosecant square, and then the remaining is a cosecant to the fourth. And this is what the cosecant to the power 2k minus 2 is all about. So the 6 here is a power to the power being a multiple of 2, and then this here is that power 2k minus 2 because we have separated out a power 2 out here. And there's dx. All right. So from now, right at this step right here, we can observe that the power 4 on this cosecant can be rewritten as the cosecant squared of x, but further squared. Okay. And that other factor here is a cotangent cube of x, and then we're still going to have that cosecant square of x remains in our integral. Okay, so this is exactly what I have given out in the general video lecture, that with our cosecant being to some 2k power, and we can rewrite that as a cosecant to the 2k minus 2 of x multiplied with a cosecant square of x, and from there we're going to turn this into a cosecant squared of x and raised to the whatever power k minus 1. And that's what it is right here. This is the k minus 1, which is, in this case, we don't even have to know what that k is. The point is we extracted out a square, okay, that we put inside the parentheses. All right, so continuing into the step here, I'm going to get from our previous understanding prior to getting into this course right here, then we have a known identity. That's cotangent square of x plus 1 will equal cosecant square of x. And so right from here, I am going to take this cotangent square of x plus 1 expression to substitute for my secant square in the current expression. But be careful a little bit that I substitute that for this secant square that's inside another power, instead of substituting that for this secant square right there. So here I will rewrite my integral as cotangent square of x plus 1 substituted in for that cosecant square of x from the previous step, squared times a cotangent cube of x times a cosecant square of x. All right. And so now at this step right here, observe that we have cotangent all completely in terms of cotangent right here, except for that secant square right here. So I am now going to make a substitution where I let u to equal cotangent of x right out from that observation. So by doing this, then of course, according to the substitution that I have chosen, then du dx, the derivative of u in respect to x, will equal minus cosecant square of x, as we have learned from differential calculus. And so this will consequently bring us to du will equal minus cosecant square of x dx after rearranging the differentials. And so consequently, as one further little step here, the cosecant square of x dx will equal to minus du. I just simply divided both sides of that previous equation by a negative 1. But so now I can substitute, as said earlier, I can substitute the cotangent of x by u. And then now I can substitute, I realize that I can substitute the cosecant square of x dx, the entire differential here, with a minus du differential. So the integral now will become the integral of u squared plus 1 all squared times u cube times minus du. All right, and so at this point right here, I have turned my integral into an integral that's completely in terms of the new variable, the u variable. And with that minus sign, now I can bring that in front as a coefficient, as a negative 1 coefficient. So I have minus the integral, and then u squared plus 1 all squared times u cube du. And now with this integral at the current moment right here, I can go ahead and FOIL out that perfect square right there, making it in my next step minus and the integral of u to the 4th plus 2 u squared plus 1 times the u cube with the du. And so again, this trinomial that I have just now produced came out from foiling this perfect square right here. All right. And then further, in the next step, algebraically, I am going to distribute the u cubed into each one of my terms in the parentheses here. And allow me to combine two steps in one. So I'm also, aside from distributing that u cube, I am also going to combine to distribute that minus sign for each term here as well. So that will make it the integral of a minus u to the 7 minus 2 u to the 5th minus u cube. And now we have an integral completely term by term, free from factor form. And now we are ready to find the integral for this here, term by term. We're ready to integrate this trinomial here, term by term. So after term by term integration, my first term will become a minus 1/8 u to the 8th. My next term will become minus 2 times u to the 6th over 6, which can be reduced further, and I'll wait that into the next step. This term will become minus 1/4 times u to the 4th. And don't forget a plus c. All right. And so this integral now, for the middle term, we can rewrite it as minus 1/8 times u to the 8, but minus a 1/3 u to the 6, minus 1/4 u to the 4th, plus c. All right. And so we're near the end of the problem, but we must bring back the original variable, which was in terms of x. And so the substitution that we made was from here, where u was equal to cotangent of x. So now I'm going to substitute back the cotangent of x into each one of our u variables here. And so that will make it minus 1/8 times a cotangent of x to the 8th power minus 1/3 times a cotangent of x to the 6th minus 1/4 times the cotangent of x to the 4th plus c. So this is one way how you can write your final answer. Or more conventionally, you can write this as minus 1/8 cotangent to the 8th of x minus 1/3 cotangent to the 6th of x minus 1/4 cotangent to the 4th of x plus c. This is another way that we can write our final answer. All right, so now we are ready to be looking at the next case right here. That same integral where we have a power for the cosecant in product with a power for the cotangent. Okay, but now in this integral, I want to focus on the case where the power m right here is odd. Okay, so an integer being odd, and for integer value being odd, it means m has to be a multiple of 2 with plus 1. You can also think of m as a multiple of 2 minus 1, but for this work right here, it's better to write m as m equals a multiple of 2. That's what the 2k is for, a multiple of 2 plus 1. Okay, and so now, but still, it's going to take us into the two separate sub cases. So right now, we are, as a bigger case, we're considering the power on the cosecants being odd. But now there are two sub cases that allow me to pinpoint right here. So the first case right here, okay, the easier case, when the power on the cotangent is also odd. Okay, the power on the cotangent is also odd. Okay, so similar to this argument right here, if n is an odd number, you can write it as a some multiple of 2 plus 1. And they don't necessarily have to be the equal multiple. That's why I'm writing another 2j plus 1. Okay, so now when that's the case, our integral, we can rewrite our current integral as the following. Cosecant to the 2k plus 1 of x times the cotangent to the 2j plus 1 of x dx. Okay, and so now after clearly realizing that these are two odd powers together at the same time, I am going to purposely rewrite the integral so that I can separate out. So follow closely with what I'm about to do here on the board. For the cosecant to the 2k plus 1 power, I'm going to write that as a cosecant to the 2k power of x. The cotangent to the power 2j plus 1, I'm going to rewrite it as a cotangent only to the 2j power of x. And then the extra one, the extra cosecant of x and the extra factor cotangent of x, I'm going to separate them out. So I have another extra cosecant of x times the cotangent of x. And that's how I complete, that's the integral by far. Okay, so I have separated out one factor, so taking advantage of that odd nature right there, I separated out that one factor of the cosecant, and I also took out one extra factor of the cotangent and putting it there. Okay, and so at this point right here, think about, we have an identity that cotangent square plus 1 equals a cosecant square of x, like that. Okay, so this is well known from trigonometry, and so that means the cotangent square of x can be rearranged as cotangent square of x will be equal to cosecant squared of x minus 1. Okay, and so what can this be useful for our current problem? Okay, so that information is sort of like aside for now. So in the next step, I am going to write this cosecant to the power 2k to remain the same. So we have a cosecant to the power 2k being here. But that power cotangent to the power 2j right here, I can rewrite it as a cotangent square of x to the power j, and times with the separate cosecant of x and the cotangent of x and the dx. And so now in the next step, this cotangent square, I will substitute that by the cosecant square minus 1. Right? And so in my next step, the integral will become cosecant to the 2k of x times cosecant squared of x minus 1 in parentheses raised to the j power. Okay, and then multiply with cosecant of x, cotangent of x, and dx. All right, and so at this point right here, we can go ahead and substitute u for cosecant of x. Okay, so substituting cosecant of x with u right here, then we can have a du dx will equal a minus cosecant of x times cotangent of x, or I can rewrite this as du negative du, okay, equals cosecant of x times cotangent of x with the dx. All right, and so now I am ready to get back to my integral here after pinpointing out the substitution. So now I'm going to put all the substitutions into my current integral. So the general work here will become, so that factor there will now become a u to the 2k. Now in parentheses, I will have u squared minus 1 and quantity to the power j. Okay, and then all of that cosecant of x times cotangent of x times dx can now be substituted by minus du because of that substitution right here with a minus sign for du. Okay, and so now in that way, and I can also bring that minus sign in front of the integral, and then the integral is just simply becoming something a lot cleaner. U to the power 2k multiplied with, in parentheses, is u squared minus 1 to the j power, okay, du. And so now the importance of this now is that we have turned our integral completely in terms of u right here, and this is now eventually will be this will eventually become a polynomial completely in terms of u right here once you FOIL it out that's j power right there on this binomial, and then distributing that u to the 2k, and then we can advance this easily. Okay, advance from this step here easily as a an integral of polynomials where we can integrate term by term. All right, and so that's how we handle this case right here, where so this sub case right here, we're looking at cosecant being an odd power and cotangent is also an odd power. All right, and so now let's look at some example, one example or two to demonstrate the idea of how I work with this right here, because right here is only a general instruction. All right. All right, in this example, we are looking at a trig integral where we're having a power of a cosecant multiplied in product with a power of a cotangent. But furthermore, we recognize that we're in that case where the power on the cosecant is odd, and as well as the power on the cotangent is also odd. And so now, as instructed or as guided from the general guidelines given previously, then I can rewrite this integral as cosecant to the fourth of x times cotangent squared of x, but times cosecant of x times cotangent of x, and with the dx. And so what happened is that according to the guidance given in the general guideline given previously, then I have, once we recognize that both powers here are odd, I can separate out one power from the cosecant and one power from the cotangent, and this is everything that remains, and then this is what's separated out right there. All right, and so from previous understanding, or more specifically from trigonometry, we know that cotangent squared of x plus 1 is equal to cosecant squared of x. And then so subtracting 1 from both sides, we're looking at another identity right here as popular as this earlier one. Cotangent square of x will equal cosecant square of x minus 1. Okay, so I am going to substitute this expression for my cotangent square of x that's currently standing here. And so in that case, my integral in the next step will become the integral of cosecant to the fourth of x times now cosecant square of x minus 1. And then everything else is a cosecant of x times a cotangent of x with a dx. And so at this point right here, I can see that I have a lot of cosecants right here, and it looks like this cotangent is a derivative of some cosecant. So I can make a u substitution, and where my choice is substituting cosecant with u. So substituting u with cosecant of x right here, consequently we can have du dx to come out as minus cosecant x times cotangent of x. Rearranging the differentials here is going to produce for me du equals minus cosecant of x times cotangent of x dx. And further, I can divide both sides by the negative sign right here, making it cosecant of x cotangent of x dx will equal minus du. And so these are the consequences that came out from our substitution where we let u equal cosecant of x. And so the integral in the next step will become an integral of u to the fourth, because the cosecant in our problem is substituted by u. So cosecant to the fourth becomes u to the fourth. In parentheses, the cosecant square here will become u squared and minus 1. And then this cosecant of x in product with cotangent of x in product with dx. Now we can substitute all that by the minus du differential. Minus du. And so our integral has come out completely in terms of u. I can rearrange that minus sign in front, making it minus u to the fourth times u squared minus 1 in parentheses du. But now we have an integral completely in terms of u. And so with this integral here, I can easily distribute the u to the fourth for each one of the terms here. And so in my next step, the integral becomes minus u to the sixth minus u to the fourth du. And further, I can distribute that minus sign for each of the terms here, making it an integral of u to the fourth minus u to the sixth du. And therefore, now we are completely ready to take the indefinite integral of this u to the fourth minus u to the sixth. So the integral will come out being 1/5 u to the fifth minus 1/7 u to the 7 plus c. And then we will then substitute cosecants back into each one of our places where it has the u right here. So we're looking at 1/5 times a cosecant of x to the fifth power minus 1/7 times, in parentheses, a cosecant of x to the 7th plus c. And further, a little more conventionally, this is, by the way, at already our ending of the work right here, and that can be considered as our final answer. But a little more conventionally, we can write it as a 1/5 cosecant to the fifth of x minus 1/7 cosecant to the 7th of x plus c. And that is how we have gotten our integral, our trig integral, where it came out from an odd power of cosecant in products with an odd power of a cotangent. All right, and so now still we're working with that integral where the power on the power m on the cosecant is odd, and the power n on the cotangent is, in this case right here, even. Okay, so this is the subcase, case number 2 for this category. So now n is even. Okay, and so n is even algebraically. It means n is a multiple of 2, some multiple of 2. Okay, that's what n equals 2j is all about. Okay, so now I can rewrite this integral as cosecant of 2k plus 1. I mean cosecant to the power 2k plus 1 of x times cotangent to the power 2j of x dx. Okay, and then so now with this power being in the nature of a factor 2 times some factor j right here, I can rewrite this power 2j on the cotangent as, so I have cosecant to the 2k plus 1 of x, but now I can write this factor, as I said earlier, as cotangent squared of x, but raised to the power j dx. All right, and then again from trigonometry, we know that cotangent squared of x plus 1 equals cosecant squared of x. And so that means cotangent squared of x, right, equals cosecant squared of x minus 1. Okay, I am going to use this and substitute that for the cotangent square here in my current integral setup. So this integral will generally become cosecant to the power 2k plus 1 of x, and we're multiplying that with now cosecant squared of x minus 1, but quantity to the jth power dx. So now our integral has become an integral completely in terms of the cosecants, but powers of cosecants. And I meant power here because after foiling out that jth power of this binomial, you're gonna encounter multiple terms, but each term is simply as a power of the cosecants, and we're gonna further distribute that power here for each of the terms in there. So we're gonna have completely a polynomial, but in terms of the powers of the cosecants. And so now when you have multiple terms, after successfully foiling out and distributing out that cosecant to the 2k plus 1, you're gonna just simply integrate this overall, this overall lengthy integral term by term, and each term is a power of the secant. Each term is a power of a cosecant. Each term is a power of a cosecant. And so each term is a power of a cosecant. Then we can have a power we can use as a suggestion, as a guided instruction right here. It's most effective to use, at least for my experience right here, use the power reduction formula for each cosecant to the n of x term like that. All right, and that's how you will handle the problem like that. And then as we get into the example, you will be able to see how I use the power of reduction, and the power of reduction formula will be introduced among the examples. All right, but that is how we handled this integral, this trig integral, where we have a power of cosecant, a power of cotangent, and the power on the cosecant is odd, but the power on the cotangent is even, and that's how we handle it. And now let's look at the actual example. All right, in this example, we are looking at a trig integral where we have a power of a cosecant in product with a power of a cotangent, where we recognize that the power on the cosecant is odd, but the power on the cotangent is even. And so, according to the guidance that was given in the general guidelines previously, then from this even power of the cotangent, which is currently power of 4, I can think of cotangent to the fourth of x as cotangent square of x, all squared. And so I can rewrite my integral as cosecant cube of x times, in parentheses, cotangent square of x, all squared, and dx, with an identity that we have already known from trigonometry. Cotangent square of x plus 1 equals cosecant square of x. Subtracting 1 from both sides of this identity, we're looking at cotangent square of x can be equal to cosecant square of x minus 1. And so I am going to substitute this cosecant square of x minus 1 for the cotangent square of x inside of this parentheses before the square. And so in my next step, I can produce an integral of cosecant cube of x multiplied with, in parentheses, cosecant square of x minus 1, all squared, with a dx. And so now we have turned our integral into something completely in terms of the cosecant. And so now, as instructed from the general guideline given previously, then let's go ahead and FOIL out this high power, this perfect square right here. And so in my next step, the integral becomes cosecant cube of x, and I'm going to produce parentheses to indicate whatever the FOILed out product of this cosecant square minus 1 all squared. So FOILing that out, it will give me cosecant to the fourth of x minus 2 cosecant square of x plus 1 with a dx. And then in the next step, I can further distribute that cosecant cube into each of my terms in the parentheses here. So in the next step, the integral will become the integral of cosecant to the 7th of x minus 2 cosecant to the 5th of x plus cosecant cube of x. And now we're integrating this lengthy function right here in respect to x. There's 3 terms of cosecant, 3 terms of powers of cosecant in respect to x. And this is where we can integrate term by term, and we can use a power of reduction on each of the terms right here. And so on my computer screen over here, we have what's written down as the power reduction formula for a power of a cosecant. So the integral, the formula says the integral of cosecant to some power n of x is equal to negative 1 over n minus 1 times cosecant of n minus 2, cosecant to the n minus 2 power of x times cotangent plus n minus 2 over n minus 1 as a coefficient, multiplied with another integral but of cosecant to the n minus 2. So this is why it's called the reduction formula, because the power at this integral has been reduced by 2 steps down. cosecant to the power n minus 2 of x dx. But so, in theory, we can apply the reduction formula for all three terms here, but in my style of doing that, I will tend to only apply it one at a time, but always starting out with the highest power. So with that power 7 right here. And we can think of the integral here as three separate terms. So the first term is the cosecant to the 7th of x. And the next integral here is a minus 2 cosecant to the 5th of x. And the third term is an integral of a cosecant cube of x. And so now, as said earlier, I am going to apply the reduction formula for only the highest term for now at this step right here, and I'm leaving these two other terms the same. So with the reduction formula, we're looking at minus 1/6 times cosecant to the 5th of x times cotangent of x plus, and now I'll have 5/6 times the integral of cosecant to the 5th of x dx. And once again, that's the reason why the formula was called a reduction formula, because from power 7 as an integral of the power 7 of cosecant, now we have made some finished term with some unfinished integral, but the power on the cosecant here has been reduced by 2 steps. And then let's write down the remaining integrals right here. So minus 2, the integral of cosecant to the 5th of x, and plus the integral of the cosecant cube of x. And now in my next step, I can see that I can combine these two integrals here as a like term here. These two are just simply like terms. So in my next step, I'm going to rewrite the finished term here, negative 1/6 cosecant to the 5th of x times cotangent of x. 5/6 minus 2 will give me a minus 7/6 times the integral of cosecant to the 5th of x. And we're still going to have another unfinished integral here, cosecant cube of x dx. All right, so at this point right here, I have two integrals left unfinished. Again, these are still simply just integrals where it involves only the powers of the cosecant. So I'm going to choose to start out with the higher power over here. So I am going to apply the reduction formula again, but for this power 5 of the cosecant. And so that means in my next step, the finished term is still here, minus 1/6 cosecant to the 5th of x times cotangent of x. I'm going to leave the minus 7/6 coefficient isolated out. I'm going to produce a pair of parentheses, and everything that goes inside the parentheses here will be the work finished for using the power reduction formula on this cosine to the 5th. And so in that way, we'll have minus 1/4 cosecant to the 3rd of x times cotangent of x plus 3/4 integral of cosecant cube of x dx. And so that's the reduction formula applied on that cosecant to the 5th, on the integral of cosecant to the 5th of x. But don't forget, we're still having that unfinished integral that remains right here. Integral of cosine cube of x dx. And definitely I will distribute this negative 7/6 for each of my terms right here. So in the next step, the very beginning term right here that was already finished, I'm going to just copy it down. Minus 1/6 cosecant to the 5th of x, cotangent of x. Minus 7/6 times minus 1/4 will give me plus 7/12 24th cosecant cube of x cotangent of x minus 7/8. After multiplying these two coefficients together, I'm going to end up with minus 7/8 times the integral of cosecant cube of x. And that's after distributing the minus 7/6 into each of the terms right here. And don't forget, we still have another cosecant cubed of x, which is unfinished at the point. And so we can further combine these two integrals as combining like terms. So in my next step, the integral becomes minus 1/6 cosecant to the 5th of x cotangent of x plus 7/24 times cosecant cube of x cotangent of x plus 1/8 times the integral of cosecant cube of x. And now we can apply the reduction formula for this cosecant cube of x one more time. And the 1/8 came out simply by combining minus 7/8 with 1. So in that way, for my next step, I will have the first two terms here written down as is, minus 1/6 times cosecant to the 5th of x times cotangent of x plus a 7/24 cosecant cube of x times cotangent of x plus now a 1/8. And now I'm going to open parentheses, getting ready for the reduction formula to be used, to be applied on this particular integral. So I will have a minus 1 over 2 cosecant of x times cotangent of x plus, and now in integral, I mean 1/2 the integral of just simply a cosecant of x dx. And now, I could have mentioned earlier, but we can make note right now, we can no longer use the reduction formula for this cosecant of x, because the reduction formula we have seen was only valid for the power being 2 or higher. So now at this point right here, we have a known integral. But before getting into any of that, I will distribute this 1/8 for each of the terms here. So in my next step, the integral becomes minus 1/6 cosecant to the 5th of x times cotangent of x plus 7/24 cosecant cube of x times cotangent of x minus 1/16 cosecant of x cotangent of x, and plus a 1/16 times the integral of cosecant of x. And then, so back to what I was saying earlier, the integral for cosecant of x has a known integral. And so now back to what I was saying earlier, this integral of cosecant of x is known. And so now I can bring in a known integral. The integral of cosecant of x can be simply minus natural log of cosecant of x plus cotangent of x in absolute value plus c. And so in that way, this integral in the next step will be just that. So our complete integral is written as following. That's minus 1/6 cosecant to the 5th of x times cotangent of x plus 7/24 cosecant cube of x cotangent of x minus 1/16 cosecant of x, cotangent of x, with minus 1/16 natural log of cosecant of x plus cotangent of x in absolute value plus c. And this is the answer to the integral of cosecant cube of x times cotangent to the fourth of x.